every email that comes in. And so I use Bayes to reverse engineer because I've already measured what probability of emails that have wingdings are spam.
So, quick follow-up question on that. So we know the conditional probability for P of A given B is the probability of A intersects B divided by the probability of B, right?
Right.
So if we wanted to get probability of B given A, would it just be the probability of A intersect B divided by probability of A? Is it just the inverse?
The thing you're missing here is this whole summation problem. You've got to take all the potential outcomes of A in the denominator.
So we can't just change the denominator from B to A to look at it. We can't.
Right. No, we can't do that.
Okay.
Erica?
So going off of your spam and wingdings example, for that equation, are you saying what's the probability given that an email has wingdings and it is spam?
Say that again. What's the probability?
So the P.
I got everything except for the very last part. What's the probability?
That given an email has wingdings, it's spam.
Yes, that's what we don't know, and we need to figure it out for every email that comes through our program.
So that equation you just wrote down, the summation of all given all the.
That's what this is, and we're trying to use all of this to solve for it every time an email comes in. So let's try to flesh that example out a little bit for Teresa. Okay?
I give you one.
What?
I give you one.
Find the probability of B given A. Just a second. I've got another example I've worked out here with spam and email, so it gives us kind of dual problems. It allows us to do Bayes, and it allows us to kind of do a real problem.
Okay.
So usually we don't have the table. I'm going to draw a table so we can kind of make some sense of this. Our crosstab. So let's say we've got the probability of spam versus email, and then we have the probability of wingdings. We have wingdings and we have kind of alphanumeric. Okay. This is okay. So here's my. I can make these crosstabs, and I can have joint probabilities. I can have marginals. And so let's say we're going to do this out of 100 emails. Okay? So let's say I got 63 spam wingding emails, 7 alphanumeric wingding emails, alphanumeric spam emails. That gives me 70 total spam emails, which leaves me 30 regular emails left. That means if I have 30 left here, we've got 3 wingdings emails that are just regular email. So that gives me 66 down here. And then the last two numbers have to be 27 and 34 to fill this out. So it's possible we can get all 4 categories here, right? It's possible to get wingding spam. It's possible to get wingding email. But that's not likely. It's just possible. Does that make sense? Yeah. And typically, we've looked at our research, we've looked at our emails, and we know things like the probability of getting wingdings given that it's spam. And if we were calculating it right here, we could just look at these numbers and we see that 63 wingdings emails are spam, and the total number of spam is 70. So there's a 90% chance that the conditional probability of wingdings given that it's spam is 90%. Does that make sense? I just pulled that from the table. Now, usually we're not going to create this table, but the table makes it easier to see where these numbers are coming from. Yes?
Okay, so, and I'm sorry if I'm getting
Go ahead.
very basic about this. Why would you do 63 and 70 and not 63 and 66?
63 and 66 is the probability of getting, it's 63 and 66 is what we want to go for. That's what we're trying to figure out. Okay? We're going to do the calculation. If we have the table, if we have a crosstab table, then we don't really have to use Bayes' rule. We can just do the 63, 66.
Okay, so
But usually the information we have is the rows here, and we have to recalculate those all the time. And so we can use Bayes' rule to get to this. A computer can't look up a table and kind of do this thing, especially if the table's not fully filled out, because we're not going to use all the information from the table to make this happen. But it is, in the end, the 63 divided by 66 that we're going for.
Okay, so you're just using the crosstabs.
I'm just helping you visualize the situation by giving you the omniscient view, but then we're going to use Bayes to come to that conclusion, which is what spam filters typically do. Right? They know what percentage of the emails they got that were joint probabilities. They know what percentage had wing days and were spam. And they know what percentage were total spam. Right? So that's past information. But the thing they don't know is they just got a new email. And that new email, they don't know what it is, so they have to classify it. Right? Erica?
Sorry, I ask questions to make sure I'm understanding.
Oh, so because that's not an appropriate use of questions.
Can I ask a lot of questions?
No.
So, this equation right here, you're saying the probability that, so given that we have spam, what's the probability it has wingdings and it's 90%?
Given that it's spam, that's right. Given that it's spam, the probability that it has wingdings is 90%.
So, if you were to write P given N, or S given W,
That's what we're trying to solve for.
that would be 63 over 66.
That's right.
Given they have spam, what's the probability it has?
We're trying to solve this question. But the thing is, I've given you a table which allows you to kind of solve it just from the table. But when you have a new email come in some sense, that's changed the table. And we're using these other characteristics in the table to help us kind of solve this probability. Bayesian is about helping us update old distributions to new information. And so, but things I already know, right? I know the probability of spam. What's that? 70%, right? That's this number right here. That's the probability of spam. The probability of, what's the probability of wingdings given that it's email? There's 3 emails that have wingdings, but it's 3 as a percentage, as a subset of the 30 that are emails. Right? So the probability that it's email given that it's wingdings is 10%. Okay? And then the probability that it's just email generally is 30%. That's this 30 right here. So when I have all this information, what Bayes looks like, okay, this question right here is what we're going to answer. The probability that the spam, that we have spam, given that we know there are wingdings in the email. The probability that this email is spam, given that there's wingdings in it. That's, every time an email comes in, we say, is there wingdings? There are. What's the probability that this is spam? We have to classify it and decide whether to send it to you, the user, or not. Right? So what is this going to be equal to? This is going to be the probability of wingdings given that it's spam. It's this, and that's 0.9, multiplied by the probability that it's just spam, which is this. Then we're going to take that whole thing and we're going to divide it by all possible outcomes. So we're going to do that same thing down here, the 0.9 times 0.7, and we're going to do the 0.3 times 0.1. Okay, so this is the probability that spam is email that has wingdings, plus the probability that email is the probability that that email has wingdings. Okay, so these are all the possible wingdings outcomes. The spam and the non-spam. That has to be the base. You do all that math and you get 0.63 over 0.66, which is equal to 0.955, which is the same thing as this divided by this. Right? So you can see it in the table, 0.63 divided by 0.66. But we don't always have that information. When the new email comes in, we can't classify the new email, we only know the historical precedent of the old email, right? So we're using the other things that we do know to calculate what that email is. We do this with tests, right? With medical tests, we do it with spam emails. There's lots of different uses of Bayesian updating, okay?
So my right, I guess, explain it as, you're trying to figure out what box to put that new email in?
Yes. An email came, you don't know what it is. You know past probabilities that relate to what this thing is, but you don't know if it's spam or not. And so you're going to look for, like, there's lots of different Bayesian filters it goes through, but one of them is, does it have wingdings? And if it does, then there's a high probability of spam. If it doesn't, then there's a low probability of spam. And it's the inverse of this, it's 0.0444 or whatever, right? 1 minus the 0.09555. Yeah?
Wording this as a test question, what would that sound like without the table?
I would give you these kinds of probabilities so that you can create the equation from the paragraph. Right? So you have to know some of these probabilities. And you have to know which ones they are. You have to know this is the conditional, does that make sense?
But you wouldn't have to use Bayes then, probably, because you have all that information.
No, the information allows you to create Bayes' rule, so you can calculate probability.
But we could have done this without Bayes.
Because I gave you the full table.
Okay, so if you didn't give us
So if you don't have the table, but you just have this column of probabilities, you can still answer what is the probability of span given wingdings. Okay? That's what Bayes is used for. The hardest part about Bayes is recognizing this part. So all of the possible outcomes, right? That's the hardest part. Now, if I have limited study time, as we all do, right? Well, there's a lot of things to test in this course. I'm not going to be giving you 10 questions on Bayes out of 50. Right? So pick your battles. If this is really a struggle, we can talk and discuss it, but I want to spend the whole review session just on Bayes. Okay? Does that make sense?
Do you mind showing that B of A?
Why don't we do it later? Okay? So if you want to, we'll try to go kind of an official for an hour, asking questions and helping people with what they need to know. And then I'll stick around for people who want to stay later, and we can kind of address another Bayes problem like the one you just stated, Joseph, like the one you got here. Okay?
Okay.
I feel like there's one loose end we haven't tied up yet. I don't know what it is. No, the final's posted.
The one time.
The one time. Okay. Other questions? Now, is it true that for the most part, since you've been through these quizzes, you know kind of how I quiz, the biggest fears are around the quantitative aspects and less so about kind of the conceptual aspects? Are there, so those of you, what conceptual questions do you have? We can go back to quantitative, but
What's the hardest question you put on the test?
I'll answer that after the finals are over.
When you're looking at sources and you want to know the difference between primary, secondary, and tertiary, what's a textbook considered?
Textbook is secondary.
It is secondary.
It is secondary,
Okay.
right? Why is a textbook secondary?
Interpretation.
Yes, because you're getting an author's interpretation of whatever the primary sources were,
Okay.
right? So textbooks is secondary.
I'm supposed to argue it with you, but that's okay.
Yeah.
Technically, the art is compiling all the information, that's what a tertiary is, right? Where you just compile.
Tertiary is more indexing, right? So yes, a textbook doesn't compile. A textbook organizes and filters, right, and interprets. Whereas an index just allows you to get access to all these things. Like Google search is an index, the Dewey Decimal System, all these things are indexes to the information. That's tertiary. But whenever there's interpretation involved, that's secondary.
If I hired your firm to conduct research for me, is that primary or secondary?
That's primary, right? If you have your own original research questions, it's okay if you contract it out, it's still primary. But if you conduct the research generally, and then I buy your report, even though it's exactly what I need to know, now it's secondary. And that company's probably going to sell that report to many different groups. And we call that syndicated research.
When you purchase it.
When you purchase a report that's already done. But when you're telling them what your question is, primary.
So if you have customized a syndicate report, it would be primary?
It depends. So most of the time, if they've already conducted the research, no matter how you customize or rearrange it, it's secondary.
Because it's interpretation.
No, because it's already been done, right? And because it's already been done, then primary, one of the things that makes primary is one, you're customizing it to exactly your need, and two, it's more expensive because of that customization. Secondary is usually, even if I can take parts to get exactly my answer, because it's already been done and it's usually being sold to many sources, right? And many people get access to the data, that's usually considered
So
secondary.
if I write original questions, outsource them to you, when you show me the data you get back, that's primary. But
Yes.
if you write a report and give it to me, it's secondary.
Are you still giving me the questions? That's still, if I write a report and give it to you based on your questions, as long as I'm conducting the research. If I write you a report and I've already conducted research and I'm just answering from what I've already done, it's secondary. The question is, has the research been done already?
So what's the difference between inferential and descriptive? So like one of the questions on the quiz, right, was,
In terms of types of analysis, types of statistics, right? So descriptive is trying to understand a body of data, and that's looking at measures of location, measures of dispersion, relative points like percentiles and quartiles, interquartile range. These are all associations, correlation. These are all descriptive kinds of statistics. Okay. Inferential is trying to infer something about a population from samples. Okay, so those are fundamentally, you still will do descriptive statistics to sample data, right? So inferential is layered on top of descriptive. Okay, but inferential is all about taking a sample and inferring what's going on from the sample.
Using what
oh,
tools?
okay, so you're trying
Using descriptive statistics and hypothesis testing. Right, so I calculate my mean, that's a descriptive statistic. Then I use a comparative test, like a t-test or a z-test, to find out where it is in this distribution, and do a hypothesis test to see how likely it is that this occurred, or how likely it is, how close, is this different from that, or what's the actual mean of this population. I use these kinds of statistics to figure that out. So inferential is about inferring and comparing and making decisions, and so just descriptives is just about trying to understand what data do you have. Okay? And that's as far as we made it in this course. The later kinds of stuff, when we're talking about data science, was dealing more about predictive and prescriptive kinds of tools like simulation, optimization, that we didn't really get a chance to get to. And I'll post a summary of some of those ideas, but that's kind of that's layered on top of descriptive and inferential. Other questions? Quantitative or conceptual? So let me say one thing real quick about, whenever you take a final, most professors, they want to give you kind of softball questions to test your basic knowledge, right? So if you don't know that, that's a problem. Then they're going to give you kind of more complex questions for the more complex concepts. They're also going to give you questions that stretch your knowledge a bit, where you say, you technically have all the information you need to know to answer the question, but you need to think about that information in a new way in order to come to the answer. That's this idea of transfer of learning. So expect to be challenged on the final, but as long as you've studied the material, don't yourself out into saying, oh, I don't recognize this, so I must not know the answer, right? If it's going to be difficult, then get the other stuff done first, and it is formatted so that all the questions are viewable on one screen. Okay, so you can go back and forth and skip, all right? But when you come back to those questions where you're not familiar with it, struggle with it a little bit. Figure out, okay, what do I know that will help me answer this question? I haven't written a single question where you can't use the knowledge we've taught this semester to answer it. So don't get discouraged if it's not clear to you immediately, okay? Sometimes we get discouraged because we say, I don't recognize this because I haven't seen it before. Right? And then we lose points, or we do more poorly, or get discouraged. All these things can happen. But the reality is I'm just trying to test this important part of life, which is everything we learn in school, Well, are you going to recognize it when you see in the real world in a different combination? Does that make sense? So these are kind of the 3 levels of challenge that we're going to see. Kind of the basics, the complex stuff, and then kind of using old knowledge in new ways. Okay?
So are all the questions on the test multiple choice or
There are multiple choice and there are answers, numeric answer questions. Those are the 2 formats.
What percentage of questions do professors put on those tougher ones?
I don't know.
Spreadsheet?
It varies. But usually your bulk is going to be the complex questions. You put some basic in there so that students, you want to test kind of the low end of the distribution, and you want to test the high end of the distribution, and it's those bottom and top categories that do that. But most of the questions, the bulk of a typical exam is going to be in that middle space. But that's the tradition that I come from, right? There's certainly professors who are, it's all low end with, there's some professors where it's all low end. They're like, as long as you pass that bar, you pass the class. But I reserve the right to be able to lift the curve because I know that what I do is difficult, because if I want you all to do well in the exam, but I also, if everyone's getting 100, then I don't understand where you're at. Does that make sense?
Could you remind us how you are going to grade it? Because I remember you said an average of your quiz scores would have been on time. Test. Could you remind us?
Well, let's ask it. So we covered that at the beginning.
Did we? Okay.
And then, and you can ask again when we've kind of officially ended, and I'll go over that again.
I'm gonna post the video.
Sure.
Oh, and someone's going to post a video. Is that the video?
That's
Apparently.
Say hi. You actually did that exact dance, and I missed important information because I was laughing at you. With you. You did the dance.
Near you. Yes?
Can you describe like linear regression? Like optimization models is kind of like shady in my mind. I don't know if I fully grasp it.
So generally speaking, while we haven't really covered these topics in any kind of specificity, I don't know if I need another page or not, but I'm going to try to get another one. We have a lot of different techniques that we're talking about. So things that we haven't really addressed much. Regression, right? So regression is kind of the end topic in a course like this typically in kind of, over the last few decades. We're making changes to that because we need to know more than just regression. But regression, the main idea of regression is if you were to scatter plot a bunch of data points that coincide, right? So we could find a correlation, right, which might be something like 0.7, right? And we can draw a line through that, the best fitting line. Regression is the act of drawing that best fitting line. Okay, so correlation is a number summary, whereas regression gives you the slope of this line, okay? And I can do this I can calculate many different correlations. If this is a 3-dimensional space, right, then I might have, here's a y I want to predict, and so I have some constant plus another constant times x plus another constant, so this is b1, b2 times z. So now I have plus some kind of set of error terms. This is a regression equation. And what we've done is these are all slopes that help us find the best fit through this scatter plot of data. Okay? So we use regression much like correlation to identify relationships between variables. Okay? This is linear regression, but you can do nonlinear regressions where we're fitting curves instead of lines, or even kind of complex variables. There's all kinds of things you can do with it, but the basic idea is still the same. We're finding relationships, we're finding what's the best mathematical equation to predict this mass of data. And the more dispersed the data is, the bigger this error term gets, and the bigger this error term gets, the less fit we get. And we describe fit with this R term. So if you have an R squared of like 0.8, that's a really good fit because it can only go to 1. If it's an R squared of 0.1, that's a really poor fit unless you're in social science, right? Because people, whenever you're measuring people, people are all over the place, and so 0.1 is not a bad correlation coefficient for people. Does that make sense? But this is just coming from this correlation idea. That's why when we do the math for correlation, we use the symbol R. It's that same R that we see in the regression when we're talking about regression. Okay? So regression is like souped up correlation. Okay?
Why are the sample variance and sample standard deviation divided by n-1?
Okay, can anyone answer that for me? Why are sample variance and sample standard deviation, what should they be divided by? So they are divided, it's mathematically correct to divide n-1, but we would expect they should be divided by what? Just n, right? We want to take the distances divided by the number of distances to get the average distance, right? But we divide by n-1 when it's a sample. We wouldn't do that for a population, but we divide it by n-1 when it's a sample. Why? We have to correct for something. What are we correcting for? Anyone want to hazard an attempt at this?
You're correcting the difference between the sample mean versus the population mean.
Yeah, so we want to base these distances from the population mean, but we don't know what it is. So we use the sample mean, and since the sample mean is different from the population mean, but it's this population mean that minimizes the distances for the true population standard deviation, then we know the sample mean is going to be too small. And so we divide by a small, we take that n, subtract 1 on the denominator, which makes it a little bit larger, and mathematically we can show that n minus 1 is exactly the right correction factor. We didn't go through that in class, but that's the reason that's the right correction factor is because of a degrees of freedom argument. We've used 1 degree of freedom to calculate the mean, and so n minus 1 is the proper degrees of freedom. But it's all based on this idea that it's because the mean from the sample is different from the mean from the population, that makes our sample standard deviation a little too small, so we have to correct for it with a larger denominator.
On the final...
And all correction factors that we see, like the big hairy one we got in hypothesis testing, all correction factors we see are all a result of this exact same issue over and over and over again.
On the final, are you going to have the download like the spreadsheets with the data to run certain equations?
I have made data sets simple enough that there are problems that can occur when people have to download files and this kind of thing, and so I've made simple data sets when you're making calculations that you can quickly enter in, like 10 numbers.
On an Excel spreadsheet?
Yes, you should and can use Excel, but if you don't have access to Excel, if you know the equations, you can still do these things and get it right. Okay? With that said, there aren't a lot of problems where you have to enter in a lot of data because you have a time limit.
Go over growth rates and
Sure.
the problem sets 9 and 10 and the problem set you gave us.
So when we're talking about growth rates, okay, what's the catch with growth rates?
Geometric mean.
We want to use a geometric mean instead of a regular mean, right? So a regular mean is you sum up all of your xi's and then you divide by n, right? So that's your mean. But the geometric mean, the geo mean, is whenever we're dealing with products and percentage growth. Okay? So let's say I give you, let's say I'm running marathon. I'm running. And so the first day I run 5 miles. And the next day I run 4.9. And the next day I run 5.2. And then I'm able to push myself up to 6.3. And then 5.7. And then 7.1. And then 6.4. So this is how many miles I ran. Okay? How would I deal with that data if I'm trying to figure out how much more I'm running each day? So I can figure out the actual differences in miles and then just do a mean. I can say, this is the average amount of distance extra that the average amount of distance extra I ran each time. But that's not what I want to know. I want to know what the growth is. And whenever we have this word growth, or its opposite, okay? I don't know what's the opposite of growth. Not undergrowth. Shrinkage. So, whenever you have growth, we're usually talking about percentage growth, right? And whenever we talk about percentage growth, and we see this in business all the time, but mostly in finance when we're talking about kind of the growth of investments, whenever we're talking about growth of percentages, that's always a product. And we're dealing with products and percentages multiplied together. The appropriate way to calculate that average is with the geometric mean instead of an arithmetic mean. And so the geometric mean is equal to the nth root, if you have n options, the nth root of the product of the xi's. So this is just like a summation, but it's a product. So this is x1 times x2 times xn square root all over the nth root. So if I have 10 options, I multiply them all together, and these are the percentage growth rates. Okay? Now another way to do this, if I actually have the actual kind of final amount and the beginning amount, okay, then I can just take x of n minus x sub naught, the beginning, the n minus the beginning, okay, divided by x sub naught, So take the difference between the two divided by the beginning to get a percentage, and then take the nth root of that to get my geometric mean. That's if I have a lot of numbers, but it's not the percentage growths. I can't. So this is with the actual numbers. Then I can do it this way. What if I have growth rates? 5%, 6%, 2%. If they're growth rates, I can't use this method anymore. Then I have to use this method. Because I can't take the beginning growth rate and subtract off the end growth rate. So if it's measured in actual units of the growth, then I can do n minus beginning divided by the beginning nth root. If it's all rates, then I have to multiply all the rates together, take the nth root. Okay? And if there's a problem on the final that's related to geometric means, and I ask you to calculate something like that, then I'm going to put in multiple forms of that. So since these are percentages, then I would give you the decimal percentage as a right answer, the integer percentage as a right answer, each to 2 decimal places. And I would also include, you'll notice in the problem set, this idea of subtracting off the 1, right? I'll do it with and without the 1, because I just want you to get the calculation right and get that growth rate. But there might be 4 responses there. Does that make sense? So you don't have to worry about those issues. Conceptually, you can figure those things out.
So then if we were doing it in Excel, it would be the geomean, equals geomean, and then highlight all of our percentages?
If it's all percentage growth rates, so you could convert them to percentage growth rates and then just do a geomean on them, or you could, if it's units of growth, not percentages. If it's units of growth, you can take the n minus the starting point. Not, on the problem set we had a problem, right? You didn't want to take the 11,000 because that wasn't the starting point. That was after 1 year of growth, right? And so if you have a starting point and an ending point, you can take the n minus the beginning, divide by the beginning, and then take the nth root, right? But geomean doesn't work on that.
So if you figure, so in the problem set, I figured out the changing rates.
And then you can use geomean.
I used the geomean, but I didn't get it right.
Well, it should have been really close.
I mean, it was really close. But
And so I probably should have loosened up a little bit that, but I'm a little more loose on this than I was in the problem set. There was, okay.
So
Where are we time-wise?
7:30.
Okay, we're 4 minutes over. If you feel like you need to go, we've 80-20 rule, we've covered 80% of people's questions and things, and I'm happy to stay longer for those who want to stay.
In the problem set, we did it in 2 ways. The second way got to the answers, but originally we did like growth percentages. We normally do the new minus the old or the old. But when we did that in the problem set,
It depends on what you put there, because that's how I calculated the answer on the problem set, was old minus the new. As long as the new was the 5,000 and the 10,000,